Good day, everyone. Today, Kexin bin Tak, Layla and Yi from Group 16 will discuss the application of the Virial equation. History of Virial equation of state. The Virial equation of state was developed by Heike Kamerlingh-Onnes. In 1882, Kamerlingh-Onnes had tried various methods and principles through the Virial theorem, the van der Waals equation of state, and the principle of corresponding state. He made several attempts to derive the constancy and B in the van der Waals equation from both kinetic theory and thermodynamic considerations. He works systematically with experimental data to determine the values of these constants and express them as series expansions. Then, he uses the law of corresponding states introduced by van der Waals and determines the temperature-dependent virial coefficients, which are the representations of the equation of states. After that, he used a series approach to represent the deviations of real gases from ideal behavior. This approach was a significant step in the development of more accurate equations of state. The Virial equation is the rigorous theoretical foundation in statistical thermodynamics which provides exact analytic relations between the virial coefficients and the interactions between molecules in isolated clusters. It is describing the behavior of real gases, especially at high pressures and low temperatures, for deviations from ideal gas behavior through the use of virial coefficients. The definition of the Virial equation of state is a polynomial series in the density and is explicit in pressure and can be derived from statistical mechanics. Virial coefficients are the coefficients in the expansion of the compressibility factor πV of a gas in powers of the density 1 over V or in powers of the pressure P, and compressibility factor Z is defined as the pressure-volume product for the real gas divided by the pressure-volume product for an ideal gas at the same temperature. There are two forms of Virial equations and define the compressibility factor in two forms. Both of these equations are known as virial expansions. The parameters B, C, D are called virial coefficients. B' and B are second virial equations. C' and C are third virial equations, and so on. For a given gas, the virial coefficients are functions of temperature only. This is a 3D PPT diagram which illustrates the deviations of real gases from ideal behavior. For engineering purposes, the two virial equations are practical when convergence is very rapid. In engineering calculation, the virial equation can be truncated to 2 terms and 3 terms with second and third virial coefficients. The virial coefficients represent the deviations from ideal behavior. Therefore, the number of virial terms to be taken into account increases as the pressure increases. All in all, the Virial equation applies to gases with real gas behavior to correct the deviations from ideality. As the intermolecular forces become more significant at low temperature, real gases tend to deviate from ideal behavior and require the Virial equation with virial coefficients to determine the deviation under low temperature conditions. Moreover, the Virial equation applies to high pressure systems as the Virial equation with higher order virial coefficients is useful in modeling and predicting gas behavior. Besides, the Virial equation can be extended to describe the behavior of gas mixtures and predict the mixture properties and phase equilibria in multi-component systems. Phase equilibrium studies the behavior of gases at the critical point and understanding phase transitions and critical phenomena in various systems. Hence, the Virial equations can calculate thermodynamics properties of gases, such as compressibility factors, fugacity coefficients, and virial expansions. The following is an example to calculate the pressure exerted by 4.56 grams of nitrogen gas in a 2.25 dm cube container at 273 Kelvin by using Virial equation of state and a virial coefficient, B only. Compare the pressure obtained if nitrogen is a perfect gas. The pressure exerted by nitrogen gas is calculated by manual calculation and MATLAB. Firstly, the number of mole and molar volume of nitrogen are calculated d-unit of the viral coefficient, and the molar volume of nitrogen gas are converted so the equation becomes dimensional homogeneous. By using Virial equation, the pressure exerted is obtained. If nitrogen gas is a perfect gas, the equation used is just PVM equals RT. It is found that there is a slight error between the two pressures obtained. For MATLAB, after the variables are defined, the number of moles and the molar volume of nitrogen gas are evaluated by using the same equation in the manual calculation. For the easy use in the calculation in MATLAB, we define a new variable, Z, which is the molar volume of nitrogen gas in meter cube per mole. After that, the pressure exerted is calculated by using the Virial equation. Same with the manual calculation, the same equation is used to calculate the pressure of nitrogen gas if it is a perfect gas. The contents of our video are based on. That is all from us, presented by Group 16. Thank you.